Okay, we're recording, and hopefully, unlike the last two times, this can be done in one take.
Is your phone on silent?
Yes, yeah. Okay. So you guys don't get to have any fun with that.
Well done.
And have minion noises.
Yeah. Got some new ones now.
So, how's homework coming along?
You just decided.
I know.
What homework? Like 560 or 6?
We're not talking about 560 during 605.
But the homework due like September 9th.
I know, yeah, but
Did you assign?
Some of us
well, I mean,
have other stuff to do.
in the notes.
Oh, in the notes.
Yeah, that is the homework.
Oh.
And I know at least one of you has started.
Yes, now you got my answer that how it's coming up.
Okay, well,
Now
that's
you
good.
know.
All right.
Yes.
Anyone else?
I took a look at it while she was doing it.
Oh, okay. All right, that's something.
I asked the people that have started it how it was.
Yeah.
Wait,
Okay.
it's September 10th.
It's due September
This one
9th,
in
and
here.
it's not even September yet.
No, the
so
one
I'm
in
like,
here is due September 10th because it's a Wednesday. September 9th is a Tuesday.
Oh,
We
okay.
just had this discussion yesterday.
Wait, no, the 7th was Monday. No, 7th.
So
Seven.
on Monday.
Yeah, we did have a discussion yesterday, and we settled on the 9th.
Yes,
Well, what time? What day do I go to the doctor? Oh my gosh.
you're okay.
What
If
is
it makes you feel better, I have taken a painkiller today.
Okay, so you're just
Oh, so you've already
loopy?
done this, or-
Well, I thought it wore off, but I don't know because I don't feel that.
Okay.
That's what I thought.
So for anyone watching,
Okay,
September
I thought you were
9th.
doing- I thought you were
Um,
doing this one,
this
okay.
one.
Watch Victoria's eye.
Okay.
1-1. You can start
All right.
doing number 4 and 1-1, right?
Yeah, that's it. So that's the only problem from that section. And then for the notes the next section, which I'm covering today, which is not much in it, I put 2 problems in there in section 1.2.
Right. And then after that, there's going to be another note.
Yeah, so for Monday's class, there will be one of the problems I picked from those sections, and then that'll be it
Okay.
for the first assignment. So then you'll have, but that's why it's good to look at these problems as they come out. Because once a chapter's finished, then I give roughly a week, or maybe 9 days to finish it. Okay, so, all right. So I'll revisit this question next week as to how it's going. Okay, now before I get into the new notes from 1.2, I went back and updated the notes for 1.1 because I have in actually both sections of notes, I have some figures that show like phase portraits or plots of vector fields from today's section. And so to produce plots of vector fields, I just use MATLAB to create that. And so in the 1.1 notes, so the update to that is MATLAB code it gives it an approximate phase portrait. So at least you can see how the streamlines flow, what direction. For any two-dimensional autonomous system, so I created a function where you can specify what are your derivatives, x prime and y prime, and pass that to a function. Also, like what x and y do you want to consider for your plot, and then I show. So I have a code for a function included in there, and then the some sample lines of how you use it for one of the examples, so you can try it for other examples, and you can see that way how the figures in both sets of notes are generated. So if you downloaded the notes a while ago, like at the start of the semester, you need to go back to them on the site, and you can see that code. Of course, those of you who don't know MATLAB, it doesn't help you very much, but Although some of you who don't know MATLAB yet will, but that's what I feel comfortable using. I may be able to duplicate the same kind of thing in another language. Okay, so that's one item. The second item is how to get an implicit representation of a solution for at least a 2D dynamical system. And this is what actually comes up in the homework problem from 1.1, problem 4. So I guess maybe we started homework a little too early. So, okay. So this goes to what is called this term is introduced, in the problem, first integrals. So what you do is suppose you're given a two-dimensional dynamical system. So x prime is some given function f of x, y, and then y prime is another function g of x, y. Okay. And the goal is to find a solution of this form, big F of x and y is equal to 0. And the function, big F, is called a first integral. Okay. And so if this problem asks, are you able to find a first integral of a given system? So what you need to do is, from these two ODEs, set up a single ODE to solve, where instead of having both x and y dependent variables, where both x and y depend on t, the idea is you get a single ODE where you have y as a dependent variable, you can think of x as an independent variable. So you're getting t out of the picture. And that's why this procedure only works for an autonomous system. Because if there was a direct t dependence in there, we wouldn't be able to get this ODE that we're going to solve for big F. Okay. So how are we going to get this single ODE? What you do is first you multiply the first equation by y prime. Actually, multiply on the right. And then you multiply the second equation by x prime. Okay. But now the left sides match, so you can eliminate those and get this kind of ODE. So these two equations together give you g of xy dx minus f of xy dy is equal to 0. Now, just for notation, dx is the same as x prime, dy is the same as y prime. The reason why I switched notation to dx and dy is this is the kind of equation that you learn to solve at the beginning of your first differential equation course, so Math 285 here, for instance. So in that kind of class, this kind of ODE was written in this form using dx and dy instead of x prime and y prime. Okay, so now that you have this equation, how do you go about solving it? So there's an easy situation and a hard situation, and unfortunately in the homework, the hard situation is the one that comes up. So
you're subtracting the second one from the first one?
or I guess I'm subtracting it first from the second. Yeah, just that, because the way these are conventionally
Right.
written is something dx plus something dy equals 0.
Right.
Okay. All right. So now I'm going to go over, so this is a basic review from your first DE course. How do you go about solving something like that? So I'm going to,
We take the y prime to the other side and divide by the coefficient of y prime.
you could. Well, the thing is, there are different situations that come up, and pretty much all of them call for writing the equation in a different form.
Okay.
So because it may happen, depending on your g and f, that you could write it as y prime equal to something and they get something that's really easy to integrate. But so what I'm going to do is just going to cover for both situations possible. Okay. So so how to solve a general equation of this form, mdx plus ndy is equal to 0. And I'm just using this notation because that's actually straight out of the book we typically use for DE. So in this case, m is equal to g, n is equal to minus f. Okay. So first we hope for the easy situation. Well, okay, I'll go ahead and motivate it first. You want a solution of this form, big F of x and y is equal to 0, our first integral. And it's understood that y is some function of x, and you might not necessarily know that function explicitly, but there's a dependence. Y is a dependent variable, x is an independent variable. So what you do is you differentiate both sides of this equation with respect to x. So that gives you partial of f with respect to x plus partial of f with respect to y, dy dx is equal to 0. Or put another way, f sub x, so that's partial, that's the same thing, dx plus fy dy is equal to 0. So you want to match this form of the equation based on your hypothetical solution with this form. So if you go ahead and match those up, you need to find a capital big F. That was redundant, wasn't it? Capital F. So that df dx is equal to m, df dy is equal to n. Now the thing is, such an f does not always exist for the given m and n that you have. In fact, you can find out whether it's going to exist or not. Because I can take a first equation and differentiate both sides with respect to y. So I have fxy is equal to my. And then I'll differentiate this equation with respect to x. fyx is equal to nx. Now, fxy and fyx are the same. Mixed second partial derivatives are supposed to be equal. So what that means is you need dm dy to be equal to dn dx. And if that is the case, equation is said to be exact. So that's what we like to have happen, an exact equation. Now, in some cases, that is actually trivially true, because what happens is, suppose these two partial derivatives are not only equal, but they're actually both equal to 0. So if you can rearrange the equation so that my and nx are 0, that's a stronger form of exactness that you actually encountered in your first DE class. The equation is said to be separable. And that's the best kind of situation to have, because that means you can rearrange the equation so that if one side depends only on x and the other side depends only on y, and then you just integrate both sides and the equation is solved. So that's the simplest case, but we're going to deal with this more general situation here. So now, this leaves us with two questions to answer, and I will answer both of them. How do you go about solving the equation that if you determine that it is exact? So if you know that a big F exists, how do you actually get it? And the second item is, what if you did this check and it didn't check out? What if it is not exact? What can you do? Okay. Any questions so far before I address those two questions?
So the goal is to find first integrals and make the equation exact, and if possible, separable, like to find that it's exact.
Well, the idea is, so if the equation is not exact, we're going to make it exact.
Make it exact.
So bottom line is, we're eventually either we're going to be handed an exact equation or we're going to get one. And once we have an exact equation, however hard we have to fight to get it, then we'll go ahead and solve it. But I'll focus on the case of solving it first. Wow, my phone is really acting up. Ugh. That's kind of scary. Okay, then. Now, let's see. Okay. Okay, so for first question, solving an exact equation. So what you do is, first you have this requirement that partial of f with respect to x has to equal m. So what you do is you stipulate that you basically define big F, xy is going to be the integral of big M with respect to x. And this antiderivative I'm going to refer to as m1. That's going to be a function of x and y. But you have to tack on a constant of integration. But it's not really going to be a constant, it's just going to be something that's independent of x. So I'm going to throw in an extra term, g of y. G of y is unknown. So this is playing the role of the plus c that you get from integration. So now, this big F definitely satisfies this, because you differentiate this whole thing with respect to x, this goes away, and it cancels out the integral to give you big M. So now you got to satisfy the other requirement. You need partial derivative with respect to y to equal n. So what you get is, so I differentiate this with respect to y. So partial of m1 with respect to y plus g prime of y is equal to n. So now what you get is g of y is just going to be the integral of n minus partial of m1 with respect to y dy. And the thing to keep in mind, though, is this expression here, even though n and m1 may both depend on x, after you work all this out and simplify it, any dependence on x is supposed to cancel out. If it doesn't cancel out, that means you don't really have an exact equation. So there's no x in that, there should not be any x in that expression. So now you have your g of y, which can have an arbitrary constant, and you would actually add on a plus c. So now you can write down your big F. So your solution is big F of x and y, which is equal to the integral of m dx plus the integral of n minus the m1 dy plus constant is equal to 0. So that is your solution. Well, I suppose you want to memorize this. Of any exact equation, m dx plus m dy is equal to 0. Keeping in mind that this first integral here is m1. So big F is your first integral of your original system. Okay, so any questions about getting this first integral before we handle the problem of inexactness?
How do we get this one?
What? Oh, this?
M1, yes.
Okay. Well, the thing is, basically it comes directly from this, because I've already specified that big F is of this form,
Right.
just to satisfy this condition. So I'm just taking this and differentiating a whole thing with respect to y.
Right. Okay. To get that equal to n.
Yeah.
And then you wanna.
And now I just, the thing is, now I got to solve for g prime of y, so I just move everything over to the other side and integrate. Any other question? Okay, so that handles the first question. And now it's a matter of, what if we don't have an exact equation? What can we do about that? Actually, does anyone remember what that's called? What we do about that?
Right. Wait, what did you say?
The term
I'm
for
already there.
Sorry. Okay.
I can understand the temptation anyway. Oh.
I said I'm already there, and then he stared at me,
Oh.
and I asked him what? And I asked you what your question was.
Okay. Does anyone remember the term for what do you do about an inexact equation? To make it exact?
Undetermined coefficient, or,
No.
no, never mind.
Okay.
I'll just be quiet. My brain hurts.
Yeah, it
My
seems,
brain hurt.
okay.
Can you give us a hint?
That would be good.
You multiply through the equation by a certain something. What is that?
Oh, the integrating factor.
Yes, integrating factor. Okay. Okay.
You sound so stupid on that recording.
Okay.
I'm gonna call it out now.
That's okay.
Now, unfortunately, when I listened to that interlude in the recording last time, I couldn't really pick up very much. So.
That's probably a good thing.
Yeah.
Just when you're all talking.
Yeah. Okay. So this equation is not exact. What we do is we multiply by an integrating factor which I'm going to call mu. So the idea is I want to make sure that the equation, the new equation I get with coefficients mu m and mu n, make sure that is exact. So we need mu m, derivative with respect to y, is equal to mu n, derivative with respect to x. But then we go ahead and apply the product rule to that. So we need mu y m plus mu m y is equal to mu x n plus mu n x. Now, this is a difficult equation to solve for mu in general, but there's a couple simpler cases that we can handle. So for the first one, I'm going to assume that mu is only a function of y. So in other words, d mu dx is equal to 0. So that causes one of these terms to drop out. So now the equation that I'm left with is, if I go ahead and get rid of this term and I rearrange everything else, then I have mu y is equal to nx minus my all over m, and all that is multiplied by mu. Okay. Yeah. Now, I think the only way this is going to work, however, is this whole expression needs to be a function of only y. So if there's x and y dependence in there, you can't use this approach. Now, an alternative is, let's assume that mu is only a function of only x. So d mu dy is equal to 0. Similar idea, you just have mu x is equal to my minus nx all over n, all of that times mu. And this must be a function of only x. So if you can get either one of these to happen, that either this is a function of just x, or this is a function of just y, then you're good to go. You can use the appropriate equation, because now you have a simple, actually it's a linear separable ODE to solve. So in this first case, mu is equal to e to the integral of nx minus my over m dy. And in the second situation, mu is equal to e to the integral my minus nx over n dx. So you find an integrating factor. Often what can happen is maybe when you do this integral, you get a log in there, so you get some simplification. So then it's not as much of a monstrosity as it might seem. But then you So then you can go apply it from a procedure on the other board with mu m and mu n, filling in for plain old m and n. Okay, so nothing to it. Actually, it's pretty painful, but
They always work out.
what?
They usually like work out.
Yeah, a lot of things simplify once you get exactness. That's one of the nice things about getting exactness is that a lot of cancellation happens. But well, it's also because of the fact that a lot of problems of this form, the ones that can be solved, are solved because they're kind of contrived. So,
How do we know when to use either?
like either this or this,
Oh, yeah.
whichever one works out.
Okay. Right.
Okay.
So try both. Well,
Yeah, 'cause
try. I mean, okay.
yeah, 'cause that's actually what happens in the homework. That only one of them is workable.
Right.
Okay. Any other questions about these? Okay. Now, for certain problems, you might not have to go to all this trouble. For instance, you might be able to spot, just by looking, that the equation is separable. And so then all this is overkill. But you need to be prepared to do whatever it takes to get a first integral. And sometimes, unfortunately, it can get kind of ugly. Okay. So hopefully that gets you through that problem from section 1.1 that's about first integrals. Okay. Okay, so now we have section 1.2, and fortunately, we don't have much from this section, so we should still be able to do this during what time is left today and not be behind. Okay. Now, a vector field, that's a concept that came up in multivariable calculus, and it provides a nice way to discuss dynamical systems from a geometric point of view. So, refresh your memory, what is a vector field? All that is a function. Now, in the notes I use a bold X, but bolding is kind of difficult on the board. So I use this symbol to distinguish from other X's that I write. Okay. So it maps some domain in Rn to Rn. So it's a function that takes in several variables and outputs the same number of variables. So it just maps one vector, one n-dimensional vector to another. If I let my independent variables be a vector x, and this has components x1, x2, up to xn. So I want to write everything in terms of components. So, whoops. So big X of little x, so this is my vector field acting upon a particular vector little x, has components so the component functions of big X. Since any n-dimensional vector has n components, and each of these is a scalar valued function of these n independent variables. So, in a dynamical system, you have n dependent variables that depend on each other, and they also all depend on t. But you can actually describe any such dynamical system. You can relate each one to a vector field. So, for purposes of notation, I'll just give an example of that. So I have this two-dimensional dynamical system. Dependent variables x1 and x2. And yes, there's an independent variable t, but this is an autonomous system, so we don't actually have to write t in this. So what I can do is I can define a vector little x to consist of components x1 and x2. So then I can rewrite this dynamical system in vector form as little x prime is equal to big X of little x. So the time derivatives are defined by this vector field. So big X of little x1 and little x2 has these component functions, and actually I'll keep writing them horizontally because I've been doing that. So notice I use the superscript for component functions. So this is the two component functions of this vector field. The first one is just x1 times x2, and the second one is x1 plus x1 cubed, x2 to the fourth. Okay. Now, the reason why we have this convention of writing dynamical systems in terms of vector fields is it makes it easy to describe solutions in a geometric way. So a solution of a dynamical system written in this form as a vector field is a differentiable curve. And now by curve, the simplest way I can describe a curve is it's just a vector valued function of one variable. So one parameter, that parameter is usually identified as t. So my differentiable curve, which I'll use the notation R, which is often used in calculus. So So my differentiable curve is just a map from an interval AB in time into Rn. So my solution sits in Rn as well. And the way this differentiable curve qualifies to be a solution is the tangent vector points in the direction given by a vector field. For all t values in the curves domain. Now, a solution, synonyms for a solution, I could almost call this a solution curve. I can also call it an integral curve, but in this case, when I'm talking about, I call it integral curve, that's meant to refer to the vector field, whereas a solution or solution curve, that's referring to the actual system of ODEs. So unfortunately, there are many different terms used to describe the very same thing, this differentiable curve that satisfies the system. But since the book seems happy to use these terms all the time interchangeably, I just want to reinforce that, even if I don't use all the same terms myself. Also called a streamline. Okay. Well, I think that term is used less often in the book. Usually if the solution is meant to describe the motion of a fluid, and then the vector field, big X, is the velocity field of the fluid, that's usually when the term streamline is used. So when we're talking about fluid flow. Okay. So it could be called streamlines. And that's usually in the context of fluid flow. Okay. Because these dynamical systems come up in many different applications, like studying fluid flow, or maybe the solution X refers to some sort of force field. So the solution can be called force field lines. So there's a lot of application-dependent terms that all refer to the same thing. It's still a Dank solution. All right. So what I'll do now is I'll go through and work with a particular dynamical system, go ahead and solve it, and then we'll take a look at the streamlines or flow lines of the solution and see what kind of behavior we get. Here's my dynamical system. X prime is big X and little x. And my vector field, big X, which is again a function of two variables. So the first component function is 1/2 x1 plus x2. And the second component is minus 1/2 x2. So in other words, the dynamical system is x1 prime is equal to the first component. x2 prime is equal to the second component. Now, this particular system we can solve, but that's not always true. However, whether the system can be solved or not, we can still understand something about how the solutions behave just from a vector field alone. So I'm going to focus on the vector field to give a clear indication of its importance. Now I have a plot of a vector field in the notes, but I want to try to reproduce at least certain portions of interest here on the board. It's going to be kind of a pain, but I'll give it my best shot. So now, so it turns out that there are a couple solutions that are straight lines. So one of them is actually the x1 axis. That is a straight line solution. And do I have any color here? I'm probably going to regret this if it can't be erased, but oh well. At least that's my problem, not yours. Okay, so that's one straight line solution. And then the other straight line solution is a line x2 is equal to minus 2x1. So a slope it passes through the origin and has a slope of minus 2. And all the other solutions, it's like they're having to work around these two straight line solutions. So you have streamlines flowing like this. Okay. And this, like, not really a perfect quadrant, if you will, but that portion of the plane. And then you have streamlines coming up towards the origin on this side that skirt around the both straight line solutions. So it goes this way and this way. And similarly, you have other solutions on the other side of this line coming up from minus infinity. And then you have these solutions. So all these solutions are approaching the origin on either side of this straight line solution. And then they veer away and go off to infinity or minus infinity. So in these directions. Okay. So if you don't have, so because right now we don't have a solution of this system. But even if you don't have a solution, from plotting a vector field, you can get some idea of how solutions are supposed to behave. So the way you plot this vector field is for each vector little x that you choose, so choosing a whole bunch of points within the x1, x2 plane, what you do is you plot a normalized big X of little x, but it's not like position vectors. Normally, when you plot a vector, you put its initial point at the origin. But here what we do is we make the initial point situated at little x. So at each of these, so little x is treated as a position vector, but big X, that's your velocity vector. So you locate it at that position, and that's how you produce this plot. Now, MATLAB has a nice command I mentioned once before called Quiver, where you give it the x and y values of your position vectors, then the x and y values of your velocity vectors that are big X, and it'll go ahead and plot them and What I do in my function that I put out the code for, I go ahead and normalize this before I plot. And that's just for visual clarity, just so you can clearly see the directions in which these are going. Because if you also include the magnitude of big X and little x, you could have big vectors all over the place, overlapping everything, and you can't really see the behavior very well. But that's how I produce this figure, and you can see much better than this one in the notes. Now, is there any questions about the vector field plot? Okay. Now, so what we'll do in this case is we'll go ahead and solve this system since it can be solved, and then you can see how you can get the straight line solutions analytically. But at least you know we're supposed to be there from your vector field plot. And that's what I highlighted in the figure here, what I put in bold are the straight line solutions. So let's go ahead and solve this thing. So x1 prime is 1/2 x1 plus x2, and x2 prime is minus 1/2 x2. So how should we go about solving either one of these equations? Where should we start?
First one, if they're exact.
What?
If they're exact.
Well, we don't need to do that. Fortunately, these ODEs are simpler than those. The second equation, notice it doesn't have x1 in it at all. It only depends on x2. So this is actually the simplest kind of first order ODE, because if y prime is equal to ky, y of t is what?
Is the left-hand side big X's?
No,
Those are the left-hand side, those are little
yeah,
X's,
for
right?
big X's I would do that.
Okay,
Yeah.
okay, that's what I thought. I was just
Okay.
making sure, because they look kind of big.
Oh. I have a hard time controlling my font size. So.
Okay, I was just checking.
Okay. And what's the solution to that?
You
Yes.
just integrate the other. Oh wait, are you asking what is the actual solution?
Yes.
How was it?
All right. Something with e. Yes, there's an e.
E to the power of like 1/2. No, not 1/2. Something k.
Warmer.
One.
Not ky, but
K over two.
KT?
There's
Yes.
two something.
kt.
Oh, bam, I got that one.
And then your initial value y of 0 is what goes there. So so anyone messing with ODEs has to have this little off the top of their head, or it just gets a lot harder. So it was good that we had that little review there. So now, how can we use that over in our system?
But we used easily with x2 prime.
Yeah. So what is x2 is
Well, what's why not? Why not is one of e to the power negative 1/2
Times T.
times
Yeah.
T, which is,
And then I'll put in an arbitrary constant
okay, yeah.
here, and we'll just call it B2. I mean, yeah, it is x2 of 0, but whatever, it's a constant. Okay, so at least now we've solved that part. Now, what we can do is substitute that up here. So now we're solving equation x1 prime is equal to 1/2 x1 plus 1/2 b2 half t. Now what I'm going to do, in order to solve this kind of equation, I'm going to write this a little differently. I'm going to move the 1/2 x1 to the other side. So we have minus that equals that. Okay. Now, that 1/2 was kind of strange. Now, this kind of equation, how can we solve that? This was a standard form equation that comes up in a typical first DE course.
So then we can, do the same thing, and can we not express?
This equation doesn't solve as simply as this one. Because now we have these two terms involving x1, and we have what we have is inhomogeneity here that complicates things. Like for instance, this equation is it's not separable.
So we use the integrating.
We use the integrating factor. Now, okay, let me review that too. If you have y prime plus p of t y is equal to q of t, so this is a linear first order ODE, your integrating factor, mu, is e to the integral of p. So the integrating factor in this case is going to be e to the minus 1/2 t. So I'm going to multiply both sides of this by our integrating factor e to the minus 1/2 t. That's our integrating factor mu. So as a result of that, the left side collapses into a derivative of a product. So that's how this always works, because what we get is mu y prime of a whole thing is equal to mu q. And now you can integrate both sides. So if I apply that idea over here, I have e to the minus 1/2 t x1, the whole thing prime is equal to 1/2 b2. So I have e to the minus 1/2 t and e to the minus 1/2 t. So that's going to give me e to the minus t. Okay. All right. So now I can integrate both sides of this. So x1 turns out to be, I'm going to move this to the other side. So that's e to the t over 2 times the integral of, well, I'll pull out the 1/2 b2 times the integral of e to the minus t dt. So now we still have to, wait, something here. Oh, I'm thinking of a different problem, never mind. So, okay. So now we can go ahead and integrate that, but don't forget the plus c. So you have to keep that in mind. Okay, so now we have, what's the integral of e to the minus t?
Negative e to the minus t.
Yeah. So I have e to the t over 2, 1/2 b2, e to the minus 1/2, e to the minus t, and then you're going to have an arbitrary constant out here, and I'm just going to call that v1. So now I can go ahead and simplify this as much as I can. So x1 is equal to b1 e to the t over 2 minus 1/2 b2, and then I combine these exponents and I get e to the minus t over 2. Okay, so we have this part of our solution for x1 and this part of our solution for x2. Alright, so yeah, we're using all the, at least first order 285 stuff here. So, although math is so unforgiving that way, you gotta remember everything. Okay. So any questions about the solution process before we return to the vector field?
Yeah, one small thing, like,
Yeah.
I understand the mu over t part, like mu of t, why we did that.
Yeah.
But then the next step, you get e to the negative 1/2 t x1 prime. Like, I'm probably not taking t, so.
Oh, okay, so from here to here?
Yes.
Okay. Yeah, I mean, I glossed over that part. So what happens is when you take this equation and multiply through by mu,
Right.
okay, so I have mu y prime plus p mu y is equal to mu q.
Right.
Now, but the thing is, this, if I differentiate both sides of this, I get mu prime on the left. What's the derivative of this?
Well, derivative of e to the something is e to that something.
Yes. E to the integral p of t, but what else do I need because of a chain rule?
Derivative of,
See the, well,
so it would be pt dt.
Just p of
Just
t.
pt, yeah.
Yeah, it's a derivative of the exponent,
Right.
which is p. But this is mu. So mu prime is equal to p mu. That's how it's designed.
Right.
So now if I include that here, so this is mu prime. So this is mu y prime plus mu prime y is equal to mu q. But this is a product rule. So basically we're setting up product rule in reverse.
Okay.
So I condense this and I get mu y whole thing prime is equal to mu q.
Cool. Yes, thank you. And now, yes, of course we can do that.
Yeah, yeah. So really, if you think about what I did earlier, exact equations as opposed to inexact ones that need an integrating factor. This is a scaled down version of that. You have separable equations and then unseparable equations that need an integrating factor. Because once you get it in that form, you have a right integrating factor, effectively you can almost treat it like a separable equation in that, what do you do with a separable equation? Integrate both sides. And that's what we can do now. Okay. Okay, 8 minutes left. That'll work. Now, so we have both x1 and x2 as functions of t. But if we want to understand the solutions in a geometric way, what we have are parametric curves. Because that's how we can plot x1 and x2 as functions of t. But to understand geometrically, it can often be easier, instead of having x1 and x2 both depend on t, if we have x1 depends on x2 or vice versa. Because that makes it easier for plotting in the plane or also understanding what the graphs look like. So a helpful technique that can be done in not all cases, but it can be done in this case, is eliminating the parameter. Okay. Actually, I won't. I can erase this. Never mind. hopefully that can erase all of this. Okay. Okay. So what you can do is, so instead of x1 of t and x2 of t, you can change this to x1 depending on x2. And now, or the other way around. So either one is an option. In this example, it's going to be easier to do this one than this first one. So the way this works is you solve for t, and you substitute t of x2 into x1 of t. So in that manner, the parameter gets eliminated. Now, you might need to reverse the roles of x1 and x2, but the idea is exactly the same. So I'll illustrate that with this example. So I have x2 is equal to b2 e to the minus 1/2 t. So now we can go ahead and rearrange that and solve for t. So I have x2 over b2, and then I take the natural log of both sides. So I end up with minus 2 natural log of x2 over b2. Okay. And now x1 is equal to b1 e to the t over 2 minus 1/2 b2 e to the minus t over 2. Now, in some cases, you may not really need this full expression for t. For instance, notice here I have b2 e to the minus t over 2.
Just x2.
Yeah, that is just x2. So we don't need to substitute that in there and simplify. On the other hand, what about e to the t over 2? What I'm going to do is, because here we have e to the minus t over 2, so the easiest thing to do there is, again, not substituting s. I'm pointing this out because sometimes you might need to do this. You could try rearranging this to get e to the t over 2. So e to the t over 2, how can I express this in the simplest form possible using that? Using this equation, how can I express e to the t positive t over 2 as simply as possible, using only what's in that equation?
B2 over x2.
Sorry?
Is it b2 over x2?
Yes, it's b2 over x2, because if I divide both sides by b2, I have x2 over b2 is e to the minus t over 2. But I want e to the plus t over 2. Take a reciprocal of both sides. And taking the reciprocal negates the exponent. So now I have what I need. So now I can fill that in here. So x1 is equal to b1, b2 over x2 minus 1/2 x2. Now this form is not so convenient, but what I can do now is multiply both sides by x2 and simplify as much as I can. And actually, I'm going to do more than that. I'm going to multiply both sides by 2x2 because fractions are annoying. So what you end up with in that case is 2x1 x2 plus x2 squared is equal to 2b1 b2. And actually, if I do a little add-subtract trick, if I add and subtract x1 squared, I could write it this way.
You get a quantity squared.
x1 plus x2 quantity squared minus x1 squared is equal to 2b1 b2. This is the most convenient form to write our solution in. And now, so it's implicitly describing the solutions x1 and x2. Now, this kind of equation, where you have a difference of squares involving your variables, what kind of conic section is that? So for instance, if I had a plus sign here, this would describe an ellipse. But it's a minus, so what do I have instead of an ellipse? It's a hyperbola, because you also both are squared. If one of them was linear, it would be a, what's the other option? Write a square in a linear term. What kind of graph is that?
Parabola.
Yes, it's that would be a parabola. So, okay, so these are hyperbolae. And the graph I erased, you could actually see that in most of the solutions. However, you have, but the thing is that doesn't describe all solutions. You have a hyperbolae in most of your solutions, and you also have straight line solutions. And I'm pretty much running out of time, but so I'm going to really quickly do that, and then we're done. So if you have straight line solutions, if you go back down to here, for instance, what you can do is, so one case is b2 is equal to 0. But that just means x2 is 0 for all t. So that was one of the straight line solutions I showed you, but it's just the entire x1 axis, so that horizontal line. The other possibility is b2 is non-zero, but b1 is 0. So this whole right-hand side is 0, but what that means is you're able to divide both sides by x2. So I get 2x1 plus x2 is equal to 0. That's a line of slope minus 2 passing through the origin. So, so you can look at this as y is equal to minus 2x if you want to think in xy terms. And that's the other straight line solution that I drew. So you have to keep in mind those special cases where it fails to be, because this is only a hyperbola if b1 and b2 are both non-zero. So you consider the cases where one or the other is 0, and that gives you your straight line solutions. So not all dynamical systems necessarily have straight line solutions, but it's a good thing to look for because that can help you understand the behavior of the entire set of solutions. Okay, so on Monday we will go through the remainder of Chapter 1, which is actually rather brief, and talk more about fixed points and related things. And I'll give the last Chapter 1 homework problems out then. All right. Well, we did the whole lecture in one take.